Bosses are cool. Bosses are challenging, but in most cases, bosses are challenging because they are superior. They have better size, better speed, more animations, and usually are not tied by some pesky rules such as stamina management. Bosses are obstacles, walls on your way to break through. But what if I want something different? What if I don't want to break through a wall? What if I want to defeat an opponent? Someone of my size, someone sentient, maybe a nemesis for my role-playing character, someone who while being a boss uses the same battle combinations and mechanics as me. Not a boss battle encounter, but a duel. What is an intelligent opponent? Attempts to define intelligence or intelligent agent bear a risk of heavy psychic damage intake. Luckily, as our field of game development consists of masterful usage of smoke and mirrors, we don't need to create an intelligence. Instead, we could get away with a good automaton that pretends to be intelligent if we will manage to deceive our players. Let's imagine we met a fencing opponent on our way through location. What behaviors from him will trigger in us a notion that the opponent is, in fact, an intelligent fencer? Here is my list. The character is skilled or competent. It plays the game similar to us and seems to be aware of effective tactics. The character is reactive. It uses the information we think it can gather. For example, it dodges our attacks or is able to parry them. Similar to reactive, the character is adaptive. For example, it behaves more aggressive when it knows we have less resources. For example, our big spell is on cooldown, or changes his behaviors when we change our weapon kit. Intelligent opponent must be able to outplay us and probably must create plans to do this in advance. Intelligent opponent has some preferences or, I would say, combat habits, flags that represent his style of doing things, something that signals an existence of personality. And together with personality, I would also add some randomness, a healthy dose of unpredictability which also helps to outplay the player, a noise. Nice list. Let's work with it. The first thing I want to highlight is inconsistency. The list sort of pushes us in different directions. Reactive trait implies constant situation re-evaluation and conflicts with planning trait, which implies some long-term pattern of actions. Adaptiveness and reactiveness also imply flexibility in behaviors and untied action sequences, which softly conflicts with personality trait, as personality is exactly the opposite, establishing noticeable, repeating or similar patterns. And finally, an ability to plan and outplay the player implies calculative and accurate nature of our agent, which often is the opposite of noise and unpredictability. Paradoxes in our thought process are not a death sentence, but they serve as a red flag that we are missing something. Remember our first time of choosing technologies. Then we ask two rhetorical questions. Does our AI plan anything and is our decision mechanism discrete? Now, we might answer those questions differently. Our AI definitely plans its actions to an extent, and it uses some complex calculations to prioritize the most optimal action sequence of many. But those questions were filtering. Canceling their effect is the right way to go, but we must find new ways to limit our options. For now, the only thing I can do is to cross out unstructured script and behavior tree using personal bias design principle. What else we can think of? Let's draw some parallels. In the end, intelligence is always about decisions amount and quality. There are three levels of awareness an engineer can get about their automated decisions mechanism. Level 1. Predictable. This is a level at which every decision machine can make is straight up scripted. It can be drawn as a single scheme, and any given input produces easily calculatable results. This is the level of discrete algorithms, which we already have discussed. Level 2. Explainable. On this stage, we still can completely re-engineer any system state, especially in hindsight, using logs and extensive debugging information. But the mechanism is not discrete. We can just eyeball what the system thinks about at any given time. This is the level of utility theory, response curves, simpler side genetical algorithm selections, etc. And the third level, unpredictable, complete black box. On this level, engineer knows the principles that form machine's worldview in the long term, but no input can be calculated by anyone except the machine itself. While I would be extremely happy seeing one day a completely unpredictable behavior from an enemy I created, I accept that most probably it won't happen. This level is occupied by neural nets and high-level BDI personality-like imitations. This is a complete overkill, and I won't create an enemy with a neural network attached to it. So naturally, we are left with the second level, explainable behaviors. It is characterized by a large but predefined pool of options, and a complex but known algorithm for choosing from those options. Complex choice from a big pool of options. So my first immediate reaction is that we obviously need an abstraction for option itself. We don't know for sure now what it is, but we certainly will have something that is called plan, action, course of actions, behavior, tactic, etc. But there is another one instant association in me: weights, ratings, priorities. And here I want to pause to show you the bigger picture, a beauty of this world. I want to talk about connectivity of graphs. So let's draw an axis, then on one side we will put a happy little tree, and on the other side we will put the picture known to anyone who was bored during a lesson for once. The tree is a strictly connected graph with no quartz spare edges. If I cut any single one of these lines, the graph breaks into pieces. On the other side we schemed an everyone-to-everyone relation. This graph is so connected that to isolate a vertex from it I will need n-1 cuts. Such a connectivity in this graph means that our transition routine is minimal. We exit one state and instantly go into the next. But our decision routine is a hellish beast, because we need to choose between all the states in the graph to make a transition. And on the other hand, the tree graph, well, is a tree and is traversed as one. In a tree, our transition routine is on average pretty lengthy. We need to exit everything to the common root, then to enter everything from that common root to the target state. But our decision logic on average is minimal, because, well, we traverse a logical tree, asking minimum required questions for each branch, probably in a completely discrete manner of if statements. On the other hand, when engineering a highly connected system, we are pretty much forced to invent some non-discrete choice mechanism, because here's a table for n times n-1 values, and I really doubt you want this amount of if statements in your system. And non-discrete choice mechanism is pretty much a ranked choice in some form. There are simply not that much ideas in this field, and while a concrete implementation of ranked choice is up to us, the core idea is immovable. We need some characteristic to compare options weights, some priority calculations, because everything is a number. While we are here, I also want to highlight that our character controller uses pretty much the same logic. Remember me saying that HFSM, that is a tree, is not suited for character controllers. This is because controllers, especially fighting controllers, usually are very connected systems. No matter do you have battle stances or not, each action has at least 5 to 6 inputs available, and the two elephants in the room, parallel actions and self-interruptible actions, don't help either. So naturally our controller system invented a solution of inputs priority. Do you see it? And another important insight: imagine we are playing a Souls game and see a red phantom getting out from the hole in the floor. This phantom can be a human on the other side of the screen, but it is also an enemy. So technically speaking, nothing in this world forbids me from analyzing this unit from the perspective of enemy's implementations. Remember this picture? What are the parts of our enemy? Well, it has quite a funny structure. First, as it uses the character controller system, its arms are just a plain old state machine without any other complex algorithms. On the other hand, the decision mechanism glued to the state machine is a king of non-discrete algorithms, a neural network of unseen depth flexing with a self-teaching ability. This structure gives me hope. it serves as a proof of concept. It means that on a fundamental level, we are able to create a strong opponent without some crazy new abstractions, just plain old state machine with a much more complex input generator. And remember, we don't need to create an analog to a human, we need to create a cheap surrogate with smoke and mirrors. And while computers are much weaker in some aspects, we still have some enormous leads in other. Human's reaction time at best is about 200 milliseconds, while computer's reaction time is our frame processing interval. Humans operate their controllers in analog way with 10 ugly tentacles and barely able to input 2 equal key sequences 2 times in a row, while computer doesn't even need to use an input system and can directly manipulate such variables as input vector and action transitions. Humans process game information with an unrivaled processing power, but information they have actually is not directly a game information, it is the render of visual entities representing the game onto a physical monitor projected by a camera angle and put into humans' eyes, while computer skips all these steps and can read all the necessary parameters from memory with high precision. Even if you hate the fact that I spent 5 minutes rambling about graphs, the outcome is still an important thing. Now when we understood where we are in a global picture, we have certainty in fundamental capability to create such a solution. So let's go to the drawing board to search for abstractions. First thing we need to invent is a minimal building block of our behavior. An action or a state or something different, maybe a plan. Another important thing to say is that because our agent is still in the predictable category, we need to know what exactly it does to win. In other words, first task you need to complete is to find out how the proper combat is even played in the game you create. Luckily for me, I have some PvP experience in the genre, but if you create a shooter or a MOBA, my insights can be useless and you'll need to invent different designs. To the brainstorming. First action that immediately comes to mind is a punish move, or a payoff move. This is an action that is invoked reactively when some key conditions are met. Easiest example is if the player is completely idle and is in the zone of our hit, we can try to hit them. This is a simple case, but the family of these actions is very broad. For example, outspacing move when we understood that player is locked in some attacking animation, but we already won't be hurt by it. We can start our own attacking animation to punish them underestimating our positioning. I also want to highlight that I call them actions, but they can be modular. For example, if we are out of cheese throw charges, we can reload our shield with a long and punishable animation. In this case, it can be beneficial for us to calculate a function of punish time depending on the distance from the player, getting a result a way to estimate the radius we need to have to safely recharge. But having that radius doesn't mean that we are waiting for it to happen somehow. I can perfectly see our murder bot sprinting or even rolling from the player sometimes if it really wants its cheese back. This means that our action can have at least some nesting for us to have an action reload cheese throw, having inside two sub-actions, get distance and reload cheese charge. To these reaction moves, I would also classify the defensive mechanisms, for example, rolling out of the way of flying cheese or blocking an attack. It's hard to call a defensive roll a punishing move, but technically speaking, we use our character's abilities to negate the player's impact in the way that is beneficial for us. The next family of actions are in-between actions that don't necessarily punish anything. For example, sometimes it's beneficial just to chill a little bit, for example to replenish stamina, or to wait out some short and scary buff on the opponent. People rarely do stand robotically idle even if their objective is to waste time, so we will need some glue actions. But skilled combat is much more than just identifying and punishing players overstepping. The problem of this game style is that it kinda breaks when player chooses the passive approach. The general game theory wisdom says that if your opponent chose a strategy or tactic or playstyle far from balanced by some measurement axis, for example aggression, the best answer is often to go in the different direction but less. Surprisingly universal law, by the way, so we will probably have some measurement for our aggression, and ideally we want to scale it depending on player's behavior, and we need that aggression measurement for a whole new behaviors family. Reaction family is cool, it's nice to have a lot of answers, but Skilled combatant also offers a lot of questions. Most of the reaction moves exist because player did some mistake, but most of the mistakes exist because we proactively engineered our opponent to make them. Think of outspacing maneuver. Yes, it's nice to be exactly in the ideal unreachable spot when opponent attacks, but why we are there reliably? We are there because prior to that outspacing maneuver, we baited an attack with a careful arcing movement in and out of the player's attack reach zone. No attack would take place by mistake if we didn't bait the player into it by some active movement, so there must be some baits or some openers or some other behaviors that encourage opponents to make unoptimal choices. So what do we see? Looking at this table, I want to notice that it seems that our behavior building brick is larger than player's one. Surely we use all the same animation the player has, but we use them together with a lot of meta information. For example, we don't simply sprint, we either sprint from the player in create distance behavior, or we sprint towards the player in create pressure behavior, or we sprint around the player in some form of a glue waste time repositioning behavior. So at minimum, our behavior piece uses composition to reuse player's move node with context providing input, or we do not reuse anything and just create a whole new class reusing only animations. Second thing that came to me when I was already trying to code things down is a fundamental difference between proactive and reactive intentions. Proactive intentions are fluid. They can be a float number that characterizes itself. For example, a player lost position and enemy might have a 0.4 weight of sword attacking intention and a 0.6 weight of cheese attacking intention, and that number is dependent on a lot of things. But reactions are kinda binary. If a player already started an attacking animation before us, we don't have a weight for a roll action. If we don't want to take a hit, the weight is 1 and it can be 0.6 because there is no such thing as 0.6 roll evasion. So despite similarities, proactive intentions are very different from reactive intentions. While first ones can be measured and compared by their weights, the latter ones must be measured in a Boolean manner, and the most important reaction must be chosen by a predefined priority. For example, if a player attacked and enemy understands it can outspace the attack without blocking or rolling it, it must choose outspacing 10 times out of 10, despite rolling and blocking reactions also being triggered by player's attacking animation. Now, another important question. As we obviously have some nested plans, do we use GOP? And my answer is no. I personally want for this project. To not be an overkill, GOP needs action sequences for at least 3 actions and possibly branch and reconsider plans, etc. Maybe in a game where the enemy is pursuing us in some traps-ridden mansion with cameras, signalizations, etc. But in a duel arena environment where we solve the problem of efficient resource exchange, GOP is an overkill and I won't take time to establish it. We also need a lot of creative freedom in creation of our behaviors. There are some crazy algorithms that can be a world in itself, like some complex and branched behaviors for pursuing and pressure and stamina start player. But also, as our behaviors consist of a limited number of animations or actions, I want to trim the copying if it's possible. So here is what I thought of. I can't fully classify the structure. Think of it as a 2-layer state machine. On the lowest level, there is a pool of the smallest bricks in our structure, a class named opponent action. This is an abstraction for an action with a single animation, for example run, sprint, attack, block, etc. They are contained here, but are not connected, and are in fact thin states. Actions contain the code that updates player every frame, and they use some system input, for example a direction vector. This vector shows running actions where to run or shows attacking actions where to attack. On the middle layer, there are several behaviors. Behavior is an abstraction for a sequence of actions, for example bait attack or replenish stamina or punish aggressive roll, etc. Behaviors are simpler side fate state machines. This means that they are composed of several actions and do contain their transition logics. For example, a behavior that restores a cheese throw ability contains two actions, sprint and charge reloading. First we sprint away from the player until some unpunishable position is achieved, and then we restore the cheese. As with the case of Lex behaviors in character controller, fat controller and thin state machines are in general undesirable and are a pain to scale, but in reality I doubt we will manage to create a behavior with more than 4 actions, plus the nature of behaviors is not so scalable. I expect behaviors to be highly individual pieces of code, having only some core methods and toxic sugar in common, but holding completely different logics and internal mechanisms. And then there is another layer. So behaviors are state machines, but behaviors are also thin states for a greater state machine of the full opponent. They do not contain any transition logic to other behaviors. Instead, behavior's lifecycle is managed by a single parameter, is open to reconsiderations. If the opponent is in a lock-on animation, such as roll for example, behavior is closed for reconsiderations and no transition is happening. If behavior is open for reconsiderations, transition might happen. It is decided by the top layer of this construction, called brain. So brain is the module that processes ranked choices for our behaviors. Every frame we ask our current behavior if it is open to reconsiderations. If it is, the brain defines what action is next and initiates transition. Internally, the brain will have two pools for choice: reactions and proactions. When brain gets a request to form an opinion, first it asks every reaction in the priority order if it's triggered. The first triggered reaction is returned as the next behavior name. If no reactions are triggered, brain calculates a float intention parameter for every proaction. This is a number between 0 and 1 and often is created with some complex formulas and curves. The brain chooses the proaction with highest current intention or some random from the top 2, 3, 4, etc. to get more noisy results if we want to. That's kinda it, a 3-store system. Technically it is a hierarchical state machine, but it has completely different abstractions for different layers, and I also am proud of action reusage idea. There is no multiplication of complexity in actions amount, as each time one of behavior state machines uses, for example, sprint, it is the same sprint every time, we just feed different input vectors explained by different desires from different behaviors. This means that we have unusually simple structure here, as HFSM tend to look like a pyramid, but we actually have a nice 3-store cottage. That's it. I want to stop here and review the code in the next episode because, well, there are code to review and problems to solve, and because this video is about abstract structural design of an intelligent agent as I see it with Godot, and the next episode will be about concrete design of my agent implementing these technologies.